This theorem has an alternative proof by Pythagoras theorem. So we've already seen how angles OQP and angle ORP, they are turning out to be 90 degree, which makes the two triangles right angled. Exactly the condition which we want to make use of Pythagoras theorem. So consider triangle OQP. Here what is the hypotenuse? OP. So OP square is equal to OQ square plus PQ square. You can make this equation number 1. And consider triangle ORP. It is also a right angle triangle. You can see this angle is 90 degree. So what is the hypotenuse? It's OP again. So we write OP square is equal to OR square plus PR square. This is equation number 2. Equate the two equations because both of them are having the same LHS, which is OP square. So you get OQ square plus PQ square, that is RHS of first equation. It is equal to OR square plus PR square, the RHS of second equation. Now further we saw that OQ and OR are equal because they are radii of the circle. So OQ square OR square can get cancelled like this. So we get PQ square is equal to PR square. Now if you take square root on both sides, you get PQ equal to PR. We won't be taking the negative root because distances can never be negative. In fact, it is a scalar quantity. So PQ and PR are equal, and that's exactly what we wanted to prove, that the lengths of tangents drawn from an external point to a circle are equal. So enough of theorems, now let's move on to examples. So prove that in two concentric circles. But wait a second, do you know what concentric circles mean? Well, it's good if you know, otherwise let's quickly recapitulate. So concentric circles are circles with same center. So does it mean that they are the same circles? No, because the radius is different. So they have the same center, but they have different radii. I repeated this again, that radii means the plural of radius only. So for example, here you take these two circles, okay? So they are having, let's consider center O, a fixed point O. You make a circle, alright? Then you make another circle, but the radius remains the radius will change, the center remains the same. So these two circles are what we call concentric circles then. Okay, so this is the center O, this is C1 circle, and this is C2 circle here. And we are saying that the chord of the larger circle. So obviously by larger here we mean the circle having the longer radius. So clearly that is C2, the C2 circle. So what will be its chord, which joins the two points on the circumference of the circle C2. So let's say that this point, this chord is AB. But they're saying this touches the smaller circle. Let's say it touches the smaller circle at point P and it is bisected at the point of contact. So why are we using this terminology point of contact? Because if you look carefully, AB in a way is a tangent to your circle C1. So here P is the point of contact. You have to prove that it is bisected. Bisected means this AB is being divided into two equal lengths. That means you have to prove AP and PB equal. So that is the aim of this example, to prove AP is equal to BP. So you have to join OP first of all, join it by dashed lines. So it clearly OP is the radius. Radius of which circle? C1 or C2? Of C1. And AB is what? It is chord of the circle C2, but it is tangent to your circle C1. If it is tangent, what is the point of contact? That is point P. Alright. So now by theorem 10.1, which said that radius and tangent are perpendicular to one another, we can say that this radius OP is perpendicular to tangent AB. Alright. So here we notice that AB is a chord of C2, which I have even mentioned here. AB is a chord of C2 and OP is perpendicular to AB. So we can also say that OP bisects AB. Okay, so this is a property of circles, that if I'm having this radius perpendicular to any point on the circle, then the line which is having that point will be bisected. So we can say OP bisects AB. So the reason for this is that perpendicular from center of a circle, in this case it's circle C1. So perpendicular from this circle, that is OP, we proved this perpendicular by theorem 10.1. So perpendicular from center of a circle bisects the chord. The chord that we are referring to is of C2, which is AB. So that means if it is bisecting it, it means AP is equal to PV, hence proved. Then here we have a circle with center O. There is an external point T. From an external point, if you revise, how many tangents were we having? There were 2 tangents. So those 2 tangents are over here, TP and TQ. And the point of contact for tangent TP is P, and for TQ it is Q. And you have to prove that this angle PTQ is equal to twice of angle OPQ. So for this you need to assume one thing. So let's assume angle PTQ as x degree. Okay, do mention degrees because it's an angle, it does have units, it's not unitless. Then by theorem 10.2, what was theorem 10.2? That from an external point, if you're drawing 2 tangents to a circle, they are equal in length. So in that case, our external point is T and the 2 tangents are TP and TQ. So it means TP is equal to TQ. This is equal to TQ. So if 2 sides of a triangle turn out to be equal, what do we call this triangle then? We say that this triangle TPQ will become isosceles. And if opposite sides of any triangle are equal, then angles opposite to them are also equal. So angle opposite to the side TP is angle TQP, and angle opposite to the side TQ is angle TPQ. So even they turn out to be equal. Angle TPQ is equal to angle TQP because they are opposite angles of equal sides. So they are also equal. So if we consider triangle TPQ, we can say angle T plus angle P plus angle Q is equal to 180 degree. Why? Because sum of angles of triangle is equal to 180 degree. So this angle T we took as x. So x plus angle, instead of writing it P, you can write the full thing also, angle TPQ plus angle Q. So instead of writing TQP, we know that TQP is equal to TPQ. So I can simply replace angle TQP by angle TPQ. This is equal to 180 degree. If I take this x on the RHS and if I add these TPQ, which is appearing twice, so it becomes twice of angle TPQ, is equal to 180 degree minus x. So this means that angle TPQ is equal to 180 degree minus x upon 2, which is same as saying 90 degree because 180 by 2 minus x by 2. So 90 degree minus x by 2. So this is angle TPQ. Alright. Then if you look at angle OPT, what will this angle be? Angle OPT. This will be equal to 90 degree. Why? Because here if you notice, OP is the radius, TP is the tangent. So by theorem 10.1 we can say this tangent PT is perpendicular to the radius OP. Perpendicular, by virtue of being perpendicular, this angle becomes 90 degree, angle OPT. But wait a second, this angle OPT is further comprised of 2 angles if you look carefully. Okay, we have angle OPQ over here plus this angle TPQ. So if angle OPT is 90 degree, it means that subparts when added, that is angle OPQ plus angle TPQ, that would also give me a sum of 90 degree. Just popping some general information. Whenever the sum of any 2 angles is 90 degree, we call such angles as complementary. Just remember that. Alright, so coming back to the question, angle OPQ we don't know, but we can say it's equal to 90 degree minus angle TPQ. I'll just write over here now. So angle OPQ is equal to 90 degree minus angle TPQ. So 90 degree minus what is angle TPQ? Substitute it over here. It is 90 degree minus x by 2. If you open the brackets, you will get 90 degree minus 90 degree plus x by 2. 90 cancels, so this gives you angle OPQ as x by 2, unit being degrees. So angle PTQ was x, angle OPQ is x by 2. Why am I highlighting these two angles? Because we had to prove a relation between these two angles only. So if you look carefully now, angle PTQ is x degree. What is x? X is twice of x by 2. What is x by 2? It is twice of angle OPQ. OPQ. So hence we've proven that if angle PTQ is x, angle OPQ is half of it, or in other words, angle PTQ is just twice of angle OPQ. Then this is the last example for the day. So here we have a circle. Clearly, what is its center? You tell me. Its center is O. And here we've taken an external point T, from which how many tangents can we draw? 2 of them. So those two tangents are TP and TQ. So for this tangent, the point of contact with the circle is P, and for this tangent, the point of contact with the circle is Q. Now they have given that PQ is a chord. Chord is just any line segment joining the 2 points on the circle, and its length is given as 8 centimeters. The circle has a radius of 5 centimeters, which means if I join OP or if I join OQ, the distance will turn out to be the same, that is 5 centimeters. Then you have to find out the length of the tangent TP. That is question mark. So for that you have to first of all join OT. You can join the 2 points via dashed lines. Then you have to join it in such a way that this means such that it intersects your chord PQ at point R. Okay, you see I have joined these 2 points O and T, and now I am making it intersect this chord PQ at a point R. Okay, that's the only construction which is required as of now. Then if you look at triangle TPQ, here we see that T is an external point. How many tangents are we drawing? 2, TP and TQ. What can you say about the lengths? We can see that TP and TQ are equal in length. And that is not what I am saying. That is being said by theorem 10.2. So we can say that this triangle TPQ is isosceles. If 2 sides of a triangle are equal, the triangle becomes isosceles. Like we did in the previous examples, here also we can say that the angles opposite to equal sides will also be equal. So that means angle PTR, if you consider this angle, it is equal to angle RTQ. Okay, yeah, is it clear? So this triangle TPQ is further divided into 2 triangles, basically TPR and TRQ. So we can say that these 2 angles are equal. Give the reason: because they are opposite angles of equal sides and hence they are equal. So again we can say that TO is basically, this TO is bisector of angle PTQ. Angular bisector of angle PTQ. We saw that through theorem 10.2 only, when I was giving you some special remarks over there, that TO is angular bisector of angle PTQ. Okay, these 2 angles we proved them to be equal by CPCT. We basically proved the 2 triangles congruent, and then we say that corresponding angles are equal. So TO is angular bisector of angle PTQ. You can say this is also coming from theorem 10.2. So further we see that this OT is perpendicular to PQ. From the figure itself, actually you can make out OT is perpendicular to PQ. So if OT is perpendicular to PQ, I am basically dropping a perpendicular from center of a circle. So such a perpendicular always bisects the chord. So we can say that OT bisects the chord PQ. The reason is perpendicular from center to the chord will bisect the chord. Okay, so it bisects the chord. This is the reason. So if OT is bisecting PQ, it means it's dividing PQ into 2 equal halves, which means PR and RQ are equal. Now this entire length PQ was 8 centimeters. So if I divide it, they individually PR and RQ become equal to 4 centimeters. Then is it clear? Then you have to consider this triangle over here, OPR. Okay, triangle OPR. So here you notice that this is a right angle triangle. We've just proven this angle as 90 degree because OT was perpendicular to PQ. So here what is the hypotenuse? OP. So we can say OP square is equal to OR square plus PR square. Do we know OP? We do, so it will be 5 square. OR is what we don't know, plus PR square. So PR square will be what? PR became 4. So it will become 4 square. So OR square becomes 25 minus 16, which is 9. So if you take square root on both sides, OR becomes 3 centimeters. So this is 3 centimeters right now. Then if you look at angle OPT, what can you say about it? It is 90 degrees, okay, because by theorem 10.1, we can say the tangent to a circle TP is perpendicular to the radius of the circle, which is OP. So this angle becomes 90 degrees from here. Further, this angle OPT is made up of two angles, okay, angle OPR, this angle, plus angle TPR. So even they become complementary, their sum is also 90 degrees. So what do I do next? We just make this equation number 1. Okay. Then we shift our focus to this angle PTR. Okay, angle PTR and angle TPR. So if you look at this triangle TPR, here we've already said that if this angle is 90, obviously this will also be 90 by a linear pair. So angle TRP is already equal to 90 degrees. So it means that angle TRP plus angle TPR plus angle you can say RTP, or you can call it angle OTP as well. So we can say angle PTR is equal to 180 degree because sum of angles of a triangle is 180 degree. So if you make all the substitutions and stuff, you will realize that since this angle is already 90, so angle PTR plus angle TPR is equal to 90 degree. You make this equation number 2. What was your first equation though? Let me just write it again. That was angle OPR plus angle TPR is equal to 90 degree. Okay, angle OPR plus angle TPR. So that was equation number 1. This is equation number 2. So now we see that angle OPR, this angle, and angle TP and angle PTR, they are equal. Okay, how are they equal? If you look over here, you compare equations 1 and 2. Okay, compare 1 and 2. So you will realize that TPR is common, 90 is common. So on equating, you will realize that angle PTR is equal to angle OPR. So these two angles are equal. So if we look at this triangle TRP, and if we look at triangle PRO. So here we notice that this angle and this angle, these two angles are equal. This angle is 90, this angle is 90. So just quickly write this, that angle PTR is equal to angle OPR proven above, and you can see that angle PRO is equal to angle PRT equal to 90 degree. So by AA axiom, we can say that triangle TRP is similar to triangle PRO, that is by AA similarity criterion. So if they are similar, we can say that the corresponding sides would be in the same ratio. So we can say TP upon PO is equal to RP upon PO. You can have the other pair of sides as well, but this would suffice right now because we know OP, this is 5, again OP 5. What about RP? We found it to be 4 centimeters. So if you just substitute in stuff, you will realize that TP upon 5 is equal to 4 upon, so just make this correction, this is RO over here. So we calculated this also by Pythagoras theorem as 3 centimeters. So basically TP upon 5 is equal to 4 by 3. This is by doing nothing but just taking the ratios of similar triangles, okay, ratios of corresponding sides. So if we simplify this, you will get TP as 20 by 3 centimeters. So this is the long solution, no doubt, but it does have an alternative method. So like if you people are not very comfortable with similarity and all, then we have a straight route just using Pythagoras theorem as well. I'll just tell you that as well. So now we have an alternative way of proving this question and finding out the length TP, which is by Pythagoras theorem. So here you need to make some assumptions. So first of all, let's take TP to be equal to X. The unit can be centimeters because throughout the question we have to maintain a uniformity. So we have taken this distance to be X centimeters. Then make another assumption, which is for the side TR, and take it to be Y centimeters. Then your focus should be on triangle PRT, and here if you look carefully, I just told you how this angle PRT became equal to 90 degree. We proved that in the previous method. So that makes this triangle a right angle triangle, and here the hypotenuse would be PT. So I'll say PT square is equal to PR square plus TR square, that is by Pythagoras theorem. So if you are a person who hates similarity of triangles, this can be a good option for you. So PT we took to be X, so X square is equal to PR. We just saw how it was 4, so it will become 4 square plus TR square. So instead of TR square we can now write Y square. So X square becomes equal to 16 plus Y square, and you can make this equation number 1. Then shifting our focus to the triangle OPT, which is this triangle. This angle over here is also 90 degree. We proved it by theorem 10.1. So we can apply the Pythagoras theorem here, and the hypotenuse in this case is OT. So OT square is equal to OP square plus PT square. So OP is 5, so this becomes 5 square, plus PT will become X square, and OT, if you look carefully, that is a combination of TR and OR. In the previous method we proved OR as 3 centimeters. So OT becomes equal to OR plus RT, that is Y plus 3. So Y plus 3 whole square is equal to 5 square plus X square. Now make X square as the subjective formula. You will get X square is equal to Y plus 3 whole square minus 25. Okay, 5 square is 25, and make this equation number 2. Now if you look carefully, we can easily equate equations 1 and 2 because both of them share the same LHS, which is X square. So first and second equations imply that 16 plus Y square, we can compare the RHS now. 16 plus Y square is equal to Y plus 3 whole square minus 25. So just open this bracket over here, make use of the formula A plus B whole square, which is A square plus B square plus 2AB. So this becomes 16 plus Y square is equal to Y square plus 9 plus 6Y minus 25. You can cancel out these Y square terms, and let this 6Y be on the RHS, and you shift this 9 and 25 on the other side. So it becomes 16 minus 9 plus 25. So that means 6Y is equal to 16 minus 9 is 27, and 25 plus 7 will become 32. So your Y becomes equal to 32 by 6, or if you cancel them out, it becomes equal to 16 by 3. Unit would be centimeters. But we require the length of TP, which is X and not Y. So to reach to that stage, we can make use of equation 1. So substitute this value of Y in the first equation, and then you will get X square as 16 plus Y square, that is 16 by 3 whole square. Now that becomes 16 plus 16 square by 9. Take a 16 common, you will get 1 plus 16 upon 9. So that becomes 16 into 25 by 9. And when you solve this, you will ultimately get X as 20 by 3 centimeters. Okay, so basically if you take square root, then you will get this. So 16 square root is 4, 25 is 5, and 9 is 3. So that's how we get X as 20 by 3 centimeters. And this is of use to us because this is the length of TP, the tangent whose length we need to determine. So now time for a quick revision. Let me see how much you've gained from this lecture. So now tell me, what do you understand by a circle? So a circle is a set of points which are at a constant distance from a fixed point called the center. So that brings me to my next question. What are the parts of a circle? So we have a center, which is the fixed point. Then the boundary of that circle, if we take any point on that and we join the center of this circle, that distance is called the radius. It remains constant. Then we discussed chord. What do we mean by a chord? the line which is going to join the 2 points on any circle. Then we had the longest chord, which is the diameter. So now if you consider this shape, this is a circle. What is this point O? This point O, you tell me. Then tell me about this point P. Tell me about this distance OP. Tell me about AB. And tell me what is this RS. So label these parts of a circle. O is the center. P is just a point on the circle. OP is the radius. AB is a chord. And what is RS? It is a diameter. Then we discuss different possibilities with a circle and a line. So if we have a circle and a line, there are 3 possibilities. So there can be no common point. There can be one common point, or there can be 2 common points. So if there are no common points, we say that we are having a non-intersecting line with us with respect to the circle. If there is one common point, we call that line the tangent to the circle. If there are 2 common points, we call such a line as a secant to that circle. Now you tell me, what is this special point called in case of a tangent? It is called the point of contact. Then through different activities, what did we understand? That at any one point of the circle, we can have only one tangent. So one point and only one tangent, and we also saw the tangent is a special case of a secant where the 2 points are going to coincide and become 1 point for a tangent. So secant basically converts to a tangent, or it becomes a special case of a secant. Then we discussed 2 theorems. So theorem 1 and 2. The first theorem talked about the tangent being perpendicular to the radius of a circle, and to understand theorem 2, we understood number of tangents for a circle. So for number of tangents, we saw that we can have 0 tangents, we can have 1 tangent, we can have 2 tangents. So 0 is when the point is inside the circle. 1 when point is on the circle. And when did we get 2 tangents? When the point was outside the circle. Like this basically. So then there are 2 possibilities. We get 2 tangents. And what can you say about the lengths? By theorem 2, we can say that tangents of equal length are there for an external point. Then a quick check on you. What do you understand by concentric circles? We came across this term in one of the examples. So it's very important. So they refer to circles which are having the same center but different radii. So that's it for this chapter. Thank you.